Ignore the fourth wall.
Welcome, everyone. Thank you for joining us for Science on Tap. I see some familiar faces and some new ones. Appreciate you all coming out tonight. I want to big thank you to our partners, Radio Artifact, for providing this awesome space for us and for live streaming. Be sure to follow them on Facebook and Twitch and check out all our previous Science on Taps that are out there. Tonight we're hearing from Dr. Bayless on observing the distant universe in high definition with gravitational lensing. I've been looking forward to this talk for a while, despite the microphone problems. So I'm really excited for this event. Thank you all for being here, and I'll turn it over. About your assistant.
Yeah, no, the assistant's very high-spirited, but doesn't know the science. Let's see if we get over here. All right. Okay, well, thanks for having me. It's nice to be out here. I've known of Urban Artifact for a while, but never made it out. And part of that's because I moved to Cincinnati immediately pre-COVID with the small assistant as a baby, and so I don't know. This is the 10th time I've been out after dark since moving here. So we're trying to learn new places. That's the big plan. All right, so yeah, I'm an assistant professor in the Department of Physics at University of Cincinnati, and more specifically, I'm an observational astronomer. So I use pretty much any telescope I can get my hands on to observe the distant universe. And I think when Jen reached out, she wanted to hear a little bit about my science, but also specifically mentioned the James Webb Space Telescope as a topic of interest because it's a recent addition to the tools that we have. So I've kind of made this into two talks, one summarizing the kind of science that I do, and then sort of second half that's a brief overview of the James Webb Space Telescope, some cool stuff about its launch, and a little bit about the stuff we're starting to do with it. So we'll just jump in. All right, so a quick outline here. I've got kind of, again, three basic parts. Observational cosmology, this will be super short. The goal here is just to give you some context for the kinds of problems I work on. And then what I specifically use for my research is gravitational lensing, which allows us to magnify the distant universe. So we call gravitational lenses kind of nature's telescopes, and we point our biggest telescopes at nature's telescopes that become even more powerful. So I'll go summarize a little bit about that and I think show a few results. And then I'll start talking about James Webb because that's now the best telescope that we have. And so a lot of the really exciting stuff we can do now involves pointing James Webb, or at least the stuff that I do, involves pointing James Webb at some of these natural telescopes. So big picture cosmology, this figure, I don't even know who to credit because everyone uses it. But it's, let's see how far this thing goes. Ooh. All right. It's our kind of trumpet horn picture of the universe where we live the present day here. If you observe the universe, you can see that it's expanding, and if you track an expansion backward in time, it means that things were more and more compressed. So if you go sufficiently far back in time, then the entire universe was compressed to some incredibly high density. We'll sometimes say into an infinitely small point, but that doesn't make sense. The universe is still infinite. It's more just the density of the universe is getting higher and higher and higher, and that's what's often called the Big Bang. The kind of emergence from extraordinarily high densities to lower densities that we see today. And the big problem in cosmology is basically to understand the properties of the universe at various points in time. And because light travels at a finite speed, when you look at things that are farther and farther away, you are effectively measuring things that happen further and further in the past. So we really just kind of look at the universe in various slices, further and further away, and in each of those slices we're observing things as they were longer and longer ago. And by doing that, we can build up a picture of what the universe is made of, what happened to it, and a little bit about how physics works. And so because you're trying to look further and further back in time, and that involves looking farther away, the big frontier here, right, is to push the envelope there, view as distantly as you can. And there's some big picture questions here. There's an awful lot of science involved in cosmology. The stuff that I often work with is even two questions is brief. But a lot of what I do is related to these two questions, understanding how and when did the first stars and galaxies form. So sort of very early times, we have this dark ages. There was some period where there were no stars and galaxies, and at some point they turned on. We don't really understand how that worked. And also what physics basically governs how stars and galaxies form. And again, this just involves looking further and further back in time. So an analogy I like to use here, it's really just demographics. So we can't, travel back in time. We can't watch one particular galaxy grow and evolve and get bigger and do whatever it's doing, right? We can only just see a snapshot of lots and lots of galaxies at this very moment. And so a kind of underlying assumption here is that there's general physics that governs what happens to galaxies. And if you look at enough of them, we're randomly sampling galaxies at various points in like the typical life cycle of a galaxy. And this is kind of analogous, Cincinnati is a reasonably big college basketball city, so hopefully this makes some sense. Kind of analogous to if you wanted to understand like the human life cycle, but all you had was a photograph of like a stadium with tons of people, right? There are people in this photograph who are old, young, all different, different stages of the life cycle. You can't watch any one of them age in this picture, but if you could zoom in and make detailed studies of all the individual people in this photo, right, you could kind of build a picture maybe of what a typical person experiences and looks like throughout their life. And that's kind of what we're doing in cosmology. What I specifically use is gravitational lensing. So this is a deep field image. This is actually the first quote-unquote deep field image from the James Webb Space Telescope. So we're looking deep into the universe. And what's different from the image I showed 2 slides ago, which just showed a bunch of variously colored stars and galaxies, is that you see a lot of features in this image that are really strongly distorted, right? You see these long stretched, what we call arcs, these arc-like features. And those are galaxies that have been gravitationally lensed and sort of both magnified and distorted on the sky. And so my research really is built around using these lensing systems to literally zoom in on the distant universe. And I'll go into a little bit of how this works. Now, gravitational lensing is probably not something you think about on a day-to-day basis, but you actually have the intuition to understand what we're talking about here. Because gravitational lensing is just optics. It works the same way as lenses and reflections and things work in your everyday life. So you're used to seeing like distorted images of things, right? These are images from life and art showing variously distorted, almost funhouse mirror-y kind of thing, images of various things. And these distortions are exactly what's happening with lensing, except that in these cases, what's causing the distortion is that maybe the light's traveling through one material, then it switches to another material, that causes the light's path to bend. In the case of lensing, it's the same thing, except instead of a material causing the light to bend, it's just gravity that's causing the light to bend. So it's just a different mechanism causing the light to bend. Of course, gravity is distorting space-time. This is physics, so the math is super easy, right? We just write beta equals theta minus alpha, and we're done. So beta is where an object appears in the sky. Theta is where it is intrinsically located. And alpha is just how much it's deflected. It's a deflection angle. So you just say, all right, I have an object, light's coming at me from it, but that light's path is diverted by some angle alpha, and I see it coming from some location beta. Super easy. I work in gravitational lensing, specifically that we call strong gravitational lensing. So strong gravitational lensing is the case where the math is going to quickly spiral out of control. So I'll give you a taste, and then we'll rein it back in, and it won't show up ever again. The case where this equation, beta equals theta minus alpha, if it has multiple solutions, that is, if there are multiple paths for light to travel through and reach my eye from a single origin point, then that's called strong lensing. You're seeing multiple images of the same thing, right? And so here's me, an observer. Here is some thing and in the distant universe acting as a lens, and this is some even more distant thing that has its light deflected on 2 different paths, and I see what appears to be 2 images of this one galaxy. And this also is something you see in everyday life. I mean, go to your favorite rectangular fish tank and look at things from the edge, right? You'll see multiple images of the same fish due to light that's been bent from different different paths, right? So you can this is intuitively no different, right? It's just the mechanism that's causing the bending here is gravity and not glass. All right, so here's where the math comes in. So yeah, the lens equation is super simple. As I mentioned, you have an observer, O. You observe a thing at some angle on the sky. It has some intrinsic location that's in angular units, and it's deflected by alpha. This actually turns out to the way that gravitational lensing works actually turns out to be exactly an exact match, I should say, to how a wine glass can lens a source behind it. So if you're looking at a candle in a restaurant, and this famously was discovered at a conference over drinks, right? So if you look at a candle, say on a restaurant table, and you hold up your wine glass just so, you see 3 images of the candle flame. And this is exactly analogous. This is a real gravitational lensing system in the universe. This is one image of a galaxy, this is the second image, and that's the third image, kind of merged together in exactly the same way. If you hold the wine stem exactly, so the flame is in the middle, you form the flame forms a ring, an image of a ring, which is like the Einstein ring you see in like a perfectly aligned gravitational lensing system. And you get other image configurations. Here's kind of 2 images, kind of similar to what we're seeing in the real universe. So wine glasses can actually reproduce almost all the data we see, which is kind of fun. And when we've got a system like this, what we really need to do to use it is to understand the optics. We just need to know, like, what's the shape? How is the distortion happening? If we understand what that deflection is, then we observe the beta. And if we can measure or model what alpha is, then we can solve for theta, and you know everything. And that's great. So solving for alpha is nasty. So this is where physics gets gross. This is like some vector calculus thing, operator. And the sigmas there are like things that depend on cosmology. So these are distances in the cosmological sense, and this is not a cosmology talk, but I just want to make the point that distances in cosmology are really tricky. So dA is the angular diameter distance. This is the angular diameter distance to a source. This is the angular diameter distance to a lens, and this is the angular diameter distance between the lens and the source. And so, if you take a few classes, you can solve this stuff, and it's easy. And that's all we're going to see of the math. To show how this works, kind of a video. There we go. This is a simple schematic where we're going to have, our cartoon Earth, our cartoon distant galaxy. The galaxy is emitting light rays, and this video is basically going to drop a big gravitational mass in the middle here. And as that mass gets bigger and bigger and bigger, the light rays are going to get more and more deflected. And this is just, again, to show you in a rough sense how this lensing works. So you start dropping a bigger and bigger mass, a larger and larger concentration of stuff. The light rays from that background galaxy get bent more and more and more and more. They aren't really bent. They're just traveling through a space-time that's bent, but same basic thing. And eventually, once they're bent enough, you can see multiple images of the same galaxy. And this sort of pseudo-simulation is meant to emulate, this is real Hubble Space Telescope data of an actual lensing system, where we have 2 faint images of one background galaxy. So that's all that's happening here. You now have the machinery you need to understand gravitational lensing. Whoa. Okay, there we go. And the way that I got into this, research-wise, way back when I was a grad student, which is a little while ago now, was that we really set out to try and find a lot of these systems, because lensing is pretty rare. You need this pretty nice fortuitous alignment. You need an observer, some concentration of mass pretty far away, and then some source even further away that kind of lines up perfectly with the observer and that mass in the middle. So you need this chance alignment, and that just doesn't happen very often. So these systems are rare, and my big sort of break into this field was trying to find lots of these things, and we did. So the what we'll call a rogues gallery on the left, these are ground-based images from a not terribly large telescope, but that all show these extended kind of bluish, purplish, arc-like structures. Those are background lensed galaxies. All of the kind of yellowish, orangish, reddish stuff in the middle, those are galaxies in the lens themselves. Those are the galaxies that are deflecting the light. So you've got like blue stuff in the background that's being lensed by like the yellow stuff, which is kind of in the middle ground. And so we found these things in pretty easy, pretty shallow, like simple ground-based data from not very large telescopes, but they're interesting systems, so we had a lot of success getting resources to follow them up with things like Hubble. So this is just a little applet that goes through Hubble images of many of these same systems. And this particular one gets a lot, like shows up on Twitter like once a year because it looks like a smiley face. But that smiley face system, if I can just pause it where it comes up. It's just, it's this same system here. Here it's tilted on its side. But that's your ground-based image of, I think they call it the Cheshire cat lens, which I'm not a huge fan of like proper names. Its real name is SDSSJ 1038 plus 4849. Yeah, anyway, no romance in that, right? So these things, we found a lot of these things, and they've been fantastically interesting objects to follow up, and have fed a lot of science. Now, if you want to ask why do you want to find these things, let's go there. I mentioned we want to do galaxy demographics, and so this is one of the Hubble deep fields, so one of the, until recently, deepest images of the universe that we had. Webb has kind of blown this away, but I had the figure ready to go, so we're just going to work with this. If we want to understand galaxy properties, what we really want to be able to do is resolve a lot of fine structure. And for galaxies that are pretty close by, that's easy to do, right? You look at all these big galaxies that show up at the top of the image. If you kind of look into that image, you can see a lot of substructure there, right? Those galaxies aren't just like one fuzzy blob. You can see shapes, like spiral structures. You can see color gradients. you can measure what's going on inside of those galaxies. And those are really reasonably local. But even with Hubble, if you go into the distant universe and find some spot that's like a bunch of really distant galaxies, look and zoom in on those. And these are in principle the same kinds of galaxies, they're just much further away. And we can't resolve any of that internal structure. And so we just kind of have to average them together and say, all right, we're just gonna assume we can figure out what's going on in there, but it's all, the information's a little bit washed out. And so lensing, because it's literally a magnifying effect, is a way to get around this limitation in the very distant universe. You can point, say, Hubble or James Webb at a gravitational lens and get a much more zoomed in version of these distant galaxies. So a great example of this is another good system. I give the real name is on this one, SDSSJ 1110 plus 6459. Fantastic name. It's a really, really nice high magnification system. You see 3 images, A1, A2, A3 of a single background galaxy. If you solve for the lensing, solve all that math that showed up a few slides ago, and reconstruct what this galaxy looks like sort of without the lensing distortion, you get this source reconstruction that we've shown here. So this is a galaxy that in the previous deep field image would show up as just one of these little fuzzy blobs. But now, by pointing Hubble at a gravitational lens, we see, one, a nice disc-like structure kind of on its edge, but then there are actually like dozens of little resolved individual structures that all have, in principle, different properties. And so we're able to go into this galaxy and kind of pick it apart and understand what's inside of it in a way that would otherwise be impossible. And so science example of that, if you wanted to, for instance, understand how stars form on really small scales, one thing you might measure is what's called clump star formation, which is what this is a plot of. It's a plot of how big a clump is, radius, versus how many stars it's forming. That's on the y-axis. And the local universe, like our own Milky Way galaxy and stuff, all these little gray plus signs are things that are measured in the local universe. And the key takeaway is that if you just look at the radius axis, all these little plus signs, they span the whole range of radius, right? This is everything from, in parsecs are not a unit we need to worry too much about, but in some units of parsecs, this goes all the way from 10 to about 1,000. So like many orders of magnitude in terms of the range that these structures can have in terms of size. In the distant universe, all the colored points are measurements that were made in the distant universe. And prior to this paper, which is by a collaborator, Brian Tracy Johnson, all of the colored measurements in the distant universe was basically everything except what's in the orange circle. The orange circle is the object I just showed you. And so prior to this publication, there was kind of this belief or suspicion that maybe you couldn't form structures that were super small in the distant universe, because everything we'd actually observed were in this kind of like 100 to 1,000 range. And so this one object, by just resolving all those little bead-like, point-like objects and measuring their properties, those point-like objects are the greens, all the green points inside the gold-orange circle there. This object single-handedly kind of demonstrated to everyone, like, nope, actually, there is no size scale difference in the distant universe. If you actually have the tools to resolve the structure in the distant universe, you see the same stuff that we see locally, which is kind of a big deal. So duplicate side. And just to demonstrate, sort of how effective the lensing is here, we took our source plane reconstruction image, and you could just blur it out to say, what would this look like if there was no lensing? And that on the left is what it would look like to Hubble. It looks like a yellow fuzzy blob. And even in the middle here, this is what it would look like to the James Webb Space Telescope without lensing. So even Webb without lensing is not going to resolve any structure inside this galaxy. But the lensing effect is giving you kind of order 100 times better zoom factor, which lets you do a lot of cool science. And I'm focusing on this one because I'm particularly excited. So I actually just have recently had an approved program in James Webb to observe this source and what it's without going into the nitty gritty in very fine detail. And so they're going to start taking data on it probably in January of 2024. So we're pretty excited to see how that looks when we can really pick it apart. So that's my lead in to James Webb. I'm going to be using it. It allows us to study these distant objects. I'm sort of ending here my overview of I guess, my science focus. And we're going to now transition into what Webb does. Not the most elegant transition, but the best you're going to get, so sorry. So what is the James Webb Space Telescope? Well, it's the premier observational facility available to us right now. I've got a couple schematics here. Looks like this thing here. Right, this is an image from the side where the primary mirror is this kind of disk structure. You'll see plenty of images of it, so don't worry if this doesn't make complete sense. That's the part that actually does the reflecting for the telescope. It's got these huge sun shields. There's a five-layer set of sun shields that point at the sort of sit between the telescope and the sun. So that keeps it very dark and it keeps it very cold. And then it has some equipment that like communicates back to Earth. And the really spectacular thing about this telescope is that one, it's really big. The diameter of that primary mirror is like 6 meters, so that's like 20 feet. I don't know what that is. Kind of this stage, maybe. The mirror would kind of fill up most of the stage. And the sun shields there, those, when they're unfolded, are actually about the size of a tennis court. So what, kind of comparable to the room we're in, right? So this is a really large thing. Like this is a pretty big facility. And when you're talking about launching something into space, we don't have rockets that can just like have an open like storage compartment the size of this room. That's not a thing. And in fact, making rockets that are really, really big gets extraordinarily expensive very quickly. So the thing that James Webb did that was new was that it folded up, packed up really tight. It's kind of what's shown here in this second bit. Was packed into a reasonably small rocket and launched into space and then unfolded itself. And we didn't really talk about this before it worked. By we, I mean astronomers. But there were like dozens of single point failures for this unfolding. There's like so many ways you could have launched this thing into space. And like 306, there you go. One thing doesn't unfold. Like, oops, that's the end of it. And the really scary thing, right, is you think about what does it mean to launch something into space? You build this incredibly precise and incredibly sensitive piece of equipment, and then you like shake the hell out of it. That's basically launch. And then you like, it works. But it did. And so what does Webb do? Well, when we observe things in the distant universe, we observe light over a whole range of wavelengths. So visible light is what your eye can see. In this arbitrarily scaled graphic, it all fits into this pretty small rainbow space. But there are ranges of light, somewhat arbitrarily named, that extend both blueward to short wavelengths and redward to long wavelengths of the visible. So gamma ray radiation is super energetic, X-ray is extremely energetic, ultraviolet's very energetic, visible is what we'll call normal. Infrared is less energetic, and then on down to microwaves and radios. So the Hubble Space Telescope, we've had it for, 33-ish years now or something? 32, I guess. Hubble works in the ultraviolet up just a little bit into the infrared. And we had a recent space telescope that was really quite tiny. Spitzer was like the mirror was this big, kind of like 0.8 meters or something. Spitzer was a telescope that operated in the near mid-infrared to like the far infrared. But the James Webb Space Telescope fills this really vast space in terms of wavelength. It just kind of reaches into the optical, and then it goes all the way out into what we call the mid-infrared, about 30 microns. And so this is a space where we haven't really had space telescope capabilities at all. And that feeds a lot of cool science. And so, again, I do my own particular science. I'm going to flash through a few slides here, just briefly summarizing what Webb was meant to do, because it was meant to do a lot of things, and I'm only an expert in a little bit of that. But there were kind of 4 broad science goals. One was, finding the first galaxies, the first generation of galaxies that formed. Another was to understand in detail how individual galaxies assemble. I'm involved kind of in both of those things. Another was to understand how individual stars and planetary systems form. I don't really work on that at all, but I find it interesting. And another was to start finding, to perform detailed studies of planets around other stars. And so we've already had tremendous success at all these. So I'll just highlight a few things here. What you're looking at is that first deep field image from Webb. And 4 galaxies in the image are kind of highlighted by little squares, and little zoom-ins are in the larger sort of thumbnail cutouts. And for each of these 4 objects, we were able to measure detailed spectra. So what's shown in these panels over here are the dispersed light from those objects, where these vertical blue and red lines are indicating atomic emission lines. So we're actually seeing light emitted directly from, in this case, hydrogen and oxygen atoms in a galaxy, in 4 galaxies that are viewed somewhere between 11 and 13 billion years ago. And so we're able to actually count up, what these galaxies are made of. How much oxygen is there? How much neon is there? To really to understand their properties in a way that's before now been impossible. In terms of resolving individual galaxies, this is the Whirlpool galaxy, I think, a pretty nearby galaxy. So here you're getting the full Webb zoom. This is in the infrared, where the galaxy looks really strange, right? You normally think of a galaxy as like blue and yellow stars. What you're seeing here is actually mostly like this sort of diffuse foggy stuff is mostly like hot dust. It's dust distributed throughout the galaxy. There is also this extremely bright point-like thing that's got like diffraction spikes in the middle. That's a supermassive black hole that sits at the middle of that galaxy. And then you get these like weird kind of what are the void structures. This is all just kind of tracing, what that galaxy is being made of in a way that again was previously not possible. If you zoomed in even further to how stars formed in, say, our own Milky Way, you've got Webb images like this, which are of really local star-forming clouds. So this is a cloud of relatively cold gas and dust, and it's literally collapsing under gravity to form new stars and new planetary systems. What Webb lets us see in the infrared is, one, the spatial structure of these things, but also in the infrared, you can kind of see through, you can see light, you can see objects that were obscured at shorter wavelengths. So infrared allows you to basically see through a lot of like obscuration and pick out what's happening inside these clouds. So we've already had tremendous success making fronts on all these things. And I'm a spectroscopist. A lot of what I do is spectroscopy, but it doesn't make for the best pictures. But if you're into spectroscopy, this is also a super cool result. This is the first Webb observation of a transiting exoplanet. So an exoplanet named WASP, 96b, transiting in front of its star. And the idea is you measure the star's spectrum when the planet's not in front of it. Then you wait till the planet is in front of it, measure the star's spectrum again, and you can see the difference. And whatever the difference is, that's the difference due to a little bit of the sun's light, of that star's light, traveling through that exoplanet's atmosphere. And that different spectrum is what's shown here, where the bumps and wiggles, these large-scale up and down features, are real things. And in fact, they correspond to real molecules, in this case, water. So this is a detection of water molecules on an exoplanet, many, many light years away, which again, not possible before Webb. All right, so Webb's empowered a lot of really cool stuff, but how did we really get there? Well, I mentioned that it's kind of groundbreaking technologically. So it's really, really big. It was constructed in, this is in Northrop Grumman, but it was constructed in a clean room at Goddard Space Flight Center, which is in Goddard, Maryland, like 20, 30 minutes north of DC. They have a really, really large clean room on Goddard. By really, really large, I mean like the size of a warehouse. But it's a clean room that like keeps the particles of dust, particles per million of dust in the air at some ridiculously low level. So it's a giant warehouse, but to go in it, you have to wear like one of these clean suits where you're wrapped in a plastic bag, basically, right? But the point is, it had to be really big. You had to have a really big clean room to do this kind of work because Webb itself is extremely large. So this is all to scale. The person on the little, what would that be called? Cherry picker? My son would know. The cherry picker truck there is lifting someone up to inspect the mirror. They're about the same distance away from the camera. So for scale, you can see how large Webb is relative to a person. It's really, really big. As I mentioned, it folds up, right? So, what's that? Bucket truck. It was a bucket truck. Thank you. Yes. We've learned a lot about trucks in the last few years. And so it's really, really big, but not just the mirror itself. As I mentioned, there's also the sun shield. These little foil layers down here. These are incredibly thin layers of just foil. Not exactly, not tin foil, but similar enough. A foil-like material that will reflect light and basically insulate the telescope from the sun, which is always going to be on the other side of the foil from the actual main telescope itself. And again, those things are tennis court sized. So this thing is huge. And I mentioned it's packed up. This is literally what it looked like, packed up into like a tube. So I don't know, this looks like one of those like icy pop things. It's kind of freaks me out that they packed it up this small. But this is what it looks like, packed into its sort of payload form, all crunched together and ready to unfold. Whoop. So Webb had to be launched from French Guiana, which is on the northern coast of South America. And that's for a number of reasons. Like one, we don't have large rocket capabilities right now in the US to like get this thing up. I think the shuttle could have done it, but we don't do the shuttle. We don't fly the shuttle anymore. So this was launched on a French Ariane rocket, Ariane 5, I want to say, out of French Guiana. The reason it's in French Guiana is you always want to launch rockets close to the equator because they get kind of a boost from the fact that the Earth is spinning. And the closer you are to the equator, the more of a boost you get. So most big rocket launch sites are as close to the equator as possible. The fun story here is that this thing had to be shipped from like Goddard, Maryland, to like Northrop Grumman in Southern California. And then they had to get it to French Guiana. And it's too big to fly on a plane. And also, you'd be too afraid of the plane crashing. So they actually shipped this thing in a boat. But a weird fun fact is they actually shipped it in 3 boats, or more specifically, one of 3 boats. And no one knew which boat had the actual James Webb. And that was to deter pirates from attempting to steal it and ransom it. Because pirates are still a problem, apparently. I know, right? The Pirates of the Caribbean, as we all know. It's true. They had to sail down the Pacific through Panama and then onto the northern coast of South America. So there were no pirates, I can assure you. The pirates didn't get it. It got to French Guiana and then it was launched. And when it's launched, this is what's supposed to happen. So this is like an artist's animation of how this thing unfolds, all the different pieces that come out. First thing is a solar panel. The solar panel is deployed by a battery. After that, you get this little communication device. The solar panel provides power once it's out. Then all these pieces have to unfold and stretch out. And everything you're looking at here happened over the course of like 3 or 4 months or something like that. But these are all the different pieces that have to assemble. It's kind of like a transformer watching it like this. And it all had to go right. Unfortunately, it did. My favorite thing is actually this real video. This is an actual footage taken from the launch rocket of that first stage deployment. So that is the real James Webb Space Telescope. That is the real Earth being very bright. And that is the real solar panel slowly just deploying as recorded by some camera attached to like a launch vehicle. But pretty amazing. It's the only footage we have at this level of detail of the actual James Webb Space Telescope. But everything went great, worked just fine. Let that wrap up. It moves pretty slowly in real life. So what does James Webb actually do in space? Well, we send it to what's called a Lagrange point, which is a gravitationally stable position at an orbit around the sun, farther away from Earth. So Earth orbits the sun, right? Webb orbits further away from the sun, and it orbits in this sort of weird oscillatory fashion. That's because there's a Lagrange point is like a pseudo-stable gravitational point. Webb has to kind of orbit around that point to stay in the right spot. And it orbits in such a way that you always have the actual telescope, sort of separated from the sun, right, by this large sun shield. And that's absolutely critical to keep it cool and functional. It turns out to make some really weird, to impose some really weird restrictions on where you can point the telescope at what time of the year. So like scheduling observations is extremely complicated because this thing doesn't have kind of infinite ability. The telescope, if this is its primary mirror, you can see it kind of pointing up, right, on the screen. It doesn't have the ability to just do this. It actually has about 5 to 10 degrees of motion ability there, which means that you're kind of limited to moving it. You can kind of pan around in this direction, but you can't really like point it, say, at the crowd in this case, which just means it's a little bit tough to schedule, but it's, whatever. That's what software is for. And so it's a really big deal, and I've got a few facts here for why. One is that it was deployed in space. This is the first time we've ever actually had this transformer thing happen in space, and it worked, which is a really big deal, both for the telescope being available, but also for our ability to build even more impressive facilities in the future and know that with confidence that we can actually get them to work. It was designed to be about 100 times more sensitive than previous observatories at the same wavelengths, and it actually performs better than that. So it exceeded expectations in terms of performance. And so we know it can accomplish its science goals. And if we really want to understand our property of the universe, the properties of our universe, and how the universe started, evolved, and came to be in its present state, then this is the facility that's gonna help us answer a lot of those key questions. It was also a big deal around the world. There was, Goddard loves to talk about all the press they got. I mentioned a lot of these slides. I think I didn't say anything verbally. I should have. The first slide, I mentioned Jane Rigby, who's now the senior project scientist for James Webb. She and I have been collaborators since when I was a grad student. She was a postdoc, and she was part of that group looking to find lots of strong lenses. So Jane has been a friend of the collaborator for a long time, and she got to meet Joe Biden and talk to him about James Webb, and that's pretty cool. Okay. I'm glad we agree. The audience agrees with me that was pretty cool. I should clarify. Okay. So yeah, the performance, as I mentioned, is better than we expected. We've got the point spread function. That's basically how sharp of an image Webb makes. It's about twice as good as the sort of minimum expectation. The pointing and guiding, so how precisely it can find one spot on the sky and stay there, that's better than expected. The throughput, which is basically sensitivity, how much light that hits the telescope actually gets recorded, that's better than expected. And as designed, it's the James. The audience asked a question: what telescope? It was a 4-year-old, so to clarify. The James Webb Space Telescope. It is limited in terms of sensitivity by what's the natural sky is what's here. That's just like ambient emission from the solar system and the galaxy and the universe. It's way outside Earth's atmosphere, and so we basically get rid of all kinds of foreground effects that limit the sensitivity of telescopes on the ground. And so I've got some really amazing pictures that kind of demonstrate things. So this is real James Webb data of Jupiter. What you're seeing here is a number of structures around Jupiter. You can see Jupiter's rings, which are really quite faint but do exist. There are small moons that I didn't even know the name of before I looked at the slide. Adrastea. I'm not a solar system astronomer. Was not familiar with Adrastea, but apparently it's a very small moon. Amalthea, also didn't know about that one. Io, a moon I did know of, is off the field of view and is so bright that it's making a diffraction spike that's like coming into the field of view of this image. It's just too bright. You can also actually see background stars and galaxies in kind of the lower quadrant of this image as well. And then in terms of Jupiter, Jupiter's structure and Jupiter itself, it's just extraordinary. So we also, looking at deep fields of galaxies, this is a comparison between Spitzer, the previous infrared space telescope that we have, that's the image on the left, the same field and the same field in the sky observed with James Webb. It almost doesn't look like the same thing, right? It's just the amount of detail and depth that Webb is giving you, it boggles the mind. And Hubble was kind of a record holder for spectacular facility for making pretty pictures to show people astronomy. So this image here is a Hubble image of that first deep field I showed you, the SMACS 0723. So that's our Hubble image of what that field looks like. And we've got this nice comparison of what the Webb image looked like of the same thing. And so the level of information you're getting from Webb, I mean, it's not, it's by no means is this incremental, right? This is just blowing it out of the water, what we could do before, both in terms of depth and again, in terms of structure. Oh, geez. Okay, yeah, I think I was gonna aim for 40 minutes, so we should be wrapping up here. And again, in terms of measuring properties of distant galaxies, we're really, there we go, doing some great work here. So this is again that deep field, and I've just highlighted a couple of the cool things. These are papers that came out within like a few months of this data being available. So zooming in on this one gravitationally lensed galaxy down here, it has a proper name, which again, I'm not the biggest fan of, but fine. It's called the Sparkler Galaxy because it kind of looks like a sparkler, I guess, I don't know. But this is one of these structures where, similar to the objects of my own research that I focused on earlier, you're resolving tons of little bright star-forming clumps, like tons of little, sort of bursts of star formation are popping out, which is telling us a lot of new physics about the scale on which stars form in these distant galaxies. And I mentioned before, there are these distant, even more distant galaxies where we can measure spectra. So this little tiny red dot down here, that's a galaxy at redshift 8.6. So that's a galaxy that is being viewed 13.2 billion, as it was 13.2 billion years ago. So when the universe was 4% of its current age. So I think for a standard human lifespan, 4% of the standard human lifespan would be somewhere between age 3 and 4. So we're viewing toddler universe here. And every single feature here highlighted in colors there, right? Those are all different atomic species that we're measuring emission lines from. So you can go into this galaxy and actually measure how much oxygen there is there, how much neon, how much hydrogen. There's actually how much nitrogen, which doesn't show up on the graphic. You can do pick apart what that galaxy is made of when the universe is only 4% of its current age, which has just been really transformative. All right. So yeah, I think that's where I had a stopping point here. With a really simple point, that James Webb is the most powerful telescope ever built. It's better than we expected. For me, I like finding nature's most powerful telescopes and pointing Webb at it, which is really kind of moving the needle in terms of what we can do. We should acknowledge the incredible amount of work that went into getting Webb up there and functional. So this was teams of hundreds. The thing was built as a collaborative effort. Instruments were built in Canada and Europe and the United States. People developed software, and then 600 people kind of worked around the clock over 4 to 6 months to get Webb commissioned and to go from that first thing unfolding to actually taking science images. Yeah, so I think that's all I had. My optimistic view into the future. I can't wait to see what we're going to do with it next. Proposal deadline for cycle 3 was literally a week ago. So I'm still kind of physically recovering from writing proposals to use this thing in the next cycle. But if you have any ideas, proposals are open to anyone. And it's a blind review process. So anyone can submit a proposal. Proposals are reviewed with no knowledge of who actually wrote the proposal. So don't feel hindered. And if you have any really good ideas, come to me and we can work together on it. All right, that's all I had. So thanks a lot. There are plenty of extra slides, I guess, if people ask the right questions.
So, you were showing the difference between an image from Hubble what it would look like without gravitational lensing and gravitational lensing.
Yeah.
It makes the object clearer than if you had a straight point to be able to view it.
Well, you mean so you all
So
right?
the image, the gravitational lensing image is clearer than if you were to see it without the gravity.
Okay, so yeah, the question is about this graphic showing what comparing a lensed image to what it would have looked like unlensed to Hubble and Webb. Does the lensing make it clearer? And the answer is sort of yes. The contingency there is assuming that you can, if we go back to those equations I showed, if you can solve the gravitational lens equations and understand how light is being deflected, which is, I'll just say this object was discovered in like 2011, and we kind of got the big results on it in 2017, and that's because there were 6 years of doing like a lot of follow-up data to reconstruct that lensing. So there's a lot of work involved in getting it to the point where the answer to your question is yes, but the answer to your question is yes. It's not trivial, but the answer can be yes. Yeah. Sure.
Could you go back to the slide about cluster sizes? Because I assure you I am very far behind you, and there are so many ways I could be wrong about this, but it seemed to be that one. Yeah. So if I understand it correctly, you're looking at the sizes of clusters as a function essentially of distance.
So this is actually so this is a measurement that if I were to use a one sentence description, so the question is kind of what's being shown in this figure. A one sentence description is like, it's an attempt to measure the physical scale on which stars form. And so if you have like one coherent gravitationally bound structure that's forming stars, you want to know how many stars is it forming and how big is it? That's what this plot's about. So the x-axis is how big is the thing, and the y-axis is how many stars is it forming. And so there's actually a lot in here. But you know, the result I focused on was just kind of where on the x-axis are points appearing.
Here's the part
Yeah.
that you're so wrong about, but it looks like you're trying to ask the question, is gravity as strong at the point at which these clusters form
Ooh.
by looking at the size of the clusters that are available? And what occurred to me was the gravitational constant also appears in your lensing equation. So if you're wrong about one
Sorry,
thing,
we've got two questions on top of one another. Okay, it's a yellow circle. The point is conceded. So sorry, yes. Can you finish the thought about the question? I'll repeat the question.
I don't know that much about that, but I mean, the gravitational constant appears both in, presumably what makes stars of a certain
Yes.
cluster
So,
size.
no. Okay. So the question is kind of what are you looking at with this when you're investigating the sizes of these things? And if I understand the question correctly, you're kind of saying, are you saying that gravity is working differently at different points in time to cause structures to be different sizes?
Well, it seems like the experiment was designed to test that, but my point is gravitational lensing is also, the extent of gravitational lensing is also controlled by the extent of what you said from the
So the lensing doesn't really affect. Okay. So there's a number. Okay. So the question is kind of you're saying something about the size of these objects, that they're gravitationally bound clusters of stars, and that gravity is involved in interpreting this plot. But you're also saying that it's confused because gravitational lensing was used to kind of make these measurements. Okay. So there's a lot to this. All right. So I'm going to say something, and then I'm going to contradict myself, then I'm going to say it again. So we know how gravity works really well. So in terms of gravitational lensing, it's actually extremely robust. We know if you have an amount of mass concentrated to a sufficient degree, it will distort space-time. Like that's general relativity. General relativity is probably the most tested theory of physics, and it always no measurement, despite many efforts, has found a problem with any general relativistic prediction. So we have a general relativity theory that, as far as we know, is ironclad. That tells us how the lensing works. The sizes of these stars, like gravity the size of these star clusters, gravity is part of it. What actually ends up being the more important thing here is what's called feedback. And so that's when you form a bunch of stars, you have a big cloud of gas, and it collapses under gravity. And again, we know how gravity works. The problem is when you collapse a cloud of gas under stars, the gas heats up. If anyone wants to sit in on my current class, I'm teaching Astrophysics 1 this semester at UC, which is the kind of senior level astrophysics course. We talk a lot about the virial theorem, which is Look it up if you're curious. It just basically tells you about how potential energy turns into kinetic energy in a gravitationally balanced system. So if that cloud of gas collapses, it loses gravitational potential energy as it collapses, and it heats up. And when it heats up, that basically pushes back against the collapse. And then as you actually form stars, stars start shining. And then stars have what are called like stellar winds. Stars that are really massive don't live very long and then explode in supernovae. And so all of these processes, stars shining, stars blowing off stellar winds, and stars exploding as supernovae, basically they act to suppress star formation, right? Because you've got a cloud of gas that's trying to collapse, and a supernova explodes next to it, it just disperses that cloud, and stars don't form. So it's more about testing those mechanisms. And the question is, like, how do those mechanisms work and how efficiently? An interesting result of this is that, if the different colors here, they're the dashed lines, these are measurements, these are fits to measurements of sources further and further back in the universe. So while we do see structures kind of at all sizes, even in the distant universe, a thing to note is that, as I mentioned, all the gray plus signs, those are like a local universe. So the dashed gray line is kind of a sort of a fit to those. But as you go to the more distant universe, at fixed size, everything is forming more stars, right? So if you look at like one spot on the x-axis, I'll try not to break the audio equipment here. If you look at, say, things here, this is 10 to the 2, so that's 100 parsecs. In the local universe, things that are that size are forming this many stars. In the high redshift universe, things of that size are forming this many stars, which is more. So there's the fact that as you go in the distant universe, the points kind of step up in the space like that, is telling you something about feedback becoming less efficient, which like we think it should. The feedback, there's a lot of physics to this. Feedback has to do with how many metals you have. And so if you haven't had time to make a lot of metals, turns out metals are like really good at sort of stimulating feedback. So stars that don't have many metals are not very good at producing feedback. So stars that don't have many metals won't be very good at stopping other stars from forming. So when you go earlier into the universe, speaking simply about this, the first stars that had to have formed shouldn't have had many metals. And so they shouldn't have been very good at stopping other stars from forming. But then as those stars exploded and died, they produce metals and inject them out. And the next generation of stars that form have more metals, and they're better at stopping other stars from forming. And so that's the result that you're seeing with the kind of dashed lines stepping down, that at some fixed size, the amount of star formation you get in an object of that size changes as you go further and further back in the universe.
Thanks very much.
Sure. So I think that was not your question, but I turned it into a different question. I answered that question.
A productive question.
There we go. That's the dream. Productive questions. Any other questions, thoughts? Yes.
So for your upcoming project with the web, two parts. First, what do you hope to investigate or uncover? And then two, how difficult is it to get your proposal accepted?
Okay. So the question was, I mentioned this object where I have an approved web program. We're going to get data starting in early 2024. The question was kind of what are we aiming to do with that program? And then the second question was it hard to get that program approved? The second question is easy to answer. The answer is yes. So the oversubscription rate, oh man, I should have. If we have bonus time, I can maybe show a pretty funny plot. The oversubscription rate for web is kind of 10 to 1. That's like broadly 9 to 1. So like 1 in every 9 proposals is accepted. Or to put it this way, people ask for 9 times as much observing time as there is, like, we schedule the telescope year by year. So in a given year, there's like a fixed amount of time to use the telescope. People ask for 9 or 10 times that. It's extremely competitive. It's a really frustrating process, but whatever, it's how it works. That was hard to get through, but I'm glad that we did. And in terms of what we're gonna do, so we've showed a lot of imaging here, but I've also showed a few of these images of like spectra where you get those atomic emission lines. So what Webb really, really does, Webb is like a spectroscopy machine. And Hubble really was about imaging. And imaging is a relatively simple thing. Like, take an image with a camera, it's a relatively simple thing to do. Dispersing light into a spectrum and measuring that in detail is a much more difficult thing to do. And then to do that, at not just one position on the sky, but at many positions on the sky simultaneously, that's an even more complicated thing for an instrument to do. What Webb has are a lot of instruments that do that. Webb has instruments that can take spectra of multiple things in the sky at once. And in particular, it has one mode that can basically drop like a rectangle on the sky. It's not quite. Assume it's about the size of like the sort of cutout here. And everywhere within that rectangle, it has little. It basically slices the sky up into individual pieces that are actually about the size of this white circle. And in each of those individual pieces, it disperses a spectrum. So you get a spectrum from each spot on the sky on the size of that circle. And note that that circle is conveniently about the same size as the resolved structures that we're seeing. So the goal of this program is to measure a spectrum from every single point along this galaxy of that size, basically. And we'll do a few things. One, a big question is to understand that I mentioned, we see galaxies in deep fields in the distant universe. They look like fuzzy blobs. With lensing, we can zoom in and pull this out. So we have there's lots of codes and analysis techniques that try to take observations of a galaxy and understand what kinds of stars are in it. And when you do that for just like one whole galaxy together, it's difficult because that galaxy contains lots of stars. And some of them probably formed recently, some a long time ago, and then some in between. And you can try to reconstruct what's called a star formation history, but it's really, really difficult. So at some level, the experiment we're doing here is to make those measurements, but on each little piece of the galaxy of that size, and say, all right, what's the star formation history of the stars in this one little spot, and that little spot, and that little spot, and that little spot, and then do that across the entire galaxy. And actually, the idea is that these bright spots here are basically stars that have just recently formed. And the more diffuse underlying emission are stars that formed longer ago. And so we can actually separate those two things apart and measure those two things separately. And then at some level, the experiment is to do that, and then add all the data together, pretend like we didn't have lensing, and try to reconstruct the star formation history from some complicated model of everything as if we didn't know the different pieces, and ask, do we get the same answer? So it's really just a proof, it's basically a test of, do the methods we currently have to understand the properties of galaxies, do they work when you actually have all the information? And so it's actually, we have 2 programs approved. I was the PI of this one, I'm a co-I of the other one, and some collaborators of mine are the PIs. And the 2 programs together, we've now formed a collaboration called Legos. Legos meaning like building pieces. So the whole idea is like building blocks of galaxies and resolving that. So we've got branding is a whole thing now in science, as it turns out. So that's the goal there, is to pick it apart, understand what it's made of, put it back together again, and then ask the question, would we have measured the same thing if we didn't have all that information? Science is about systematics, as it gets, this talk can get very boring very quickly if we're not careful. I'll bring up the fun plot now that I have a minute, if I can find it. Let's see here. So there's been an effort to kind of track, where is it? Cycle 3 talk? I'll do my best here. Oh, that's why the Wi-Fi's off. I'm trying to load up a thing on a Slack conversation, but I don't have any Wi-Fi right now. Public urban artifact. We'll see if that works. This is filling the gap in the talk. I turn off the Wi-Fi, right, because you don't want Slack notifications to pop up in the middle of the talk. Okay. Someone has created a figure every year of proposal submission statistics for these large space telescopes. I'm honestly just trying to find one of them. So I know this showed up on a few different places, and now I can't figure out where it was. Proposals? Oh yeah, proposals, that's where it was. Okay. So this, this is my collaborative Slack workspace. All right, this is a figure of time left until the deadline. And all the gray points are Hubble proposal cycles, and the red points are James Webb proposal cycles. And so if you count the number of proposals submitted as a function of time until the deadline, this is what it looks like. And the remarkable thing is that Hubble was so consistent. Like every year, it was like the same thing. And then Webb has been a little more of an adventure. So year 1 with Webb are these like open pentagons. And I like this because this started to ramp up, and then it has this like rollover, because Webb's way more complicated than Hubble, so writing a proposal is way harder. So this is basically the entire field being like, oh man, this telescope's complicated. I'm gonna have to like, I have some ideas, they're not gonna happen in time. I'm gonna drop those. And then things pick back up. And then in cycle 2, you get this effect where we learned our lesson. In cycle 2, you get like a spike and then maybe a second rollover where some ideas got jettisoned. But then in cycle 3, which the deadline was like a week ago, we're up here, which is terrifying. So apparently the field figured out how to write proposals and wrote like 50% more than they ever had before. So that's proposal writing for James Webb. So this year there were like 1,900 proposals submitted. And there are, not that many more than 1,900 astronomers in the world. So I was on 14, so I'm to blame. I only PI'd one of them, but then I have a student who PI'd another, so I wrote a lot of that one too. So I only did like 1.5 of these, but yeah, fun statistics.
One more.
Yeah.
Did you learn anything surprising from your gravitational sources themselves?
Oh, studying the lenses, like the sources. Oh yeah, so that's a whole other talk. So like when I give a colloquium at like a department, I often like my spiel like, oh, I have like 2 talks stitched together. I've used it before. I often give one talk on the magnified distant universe and another talk on the lenses themselves, because this gets to the question. I actually never fulfilled my promise. I said I was going to say something, then contradicted, and say it again. So the something I said was that we know how gravity works, but the contradiction is maybe we don't. And so lensing turns out to be a really great way to go in and try and break your theories of gravity. So we also use these systems to try and understand exactly that. The question was, I should have repeated the question. The question was, do you ever use lensing to test the properties of gravitational lensing itself? And the answer is yes. We study both the lenses, which are kind of more tests of gravity. They're tests of both gravity and most of the matter there is dark matter, which I haven't even talked about. But there are ways to test the properties of dark matter. So we do tests like that with the lenses. And then we also separately do science that's using the lenses to magnify the distant universe. So yeah, both of those things happen for sure. I have 3 PhD students. 2 of them are doing the distant universe, and 1 of them is doing the lenses right now. So that's my current effort breakdown, if that helps. Makes sense. Other thoughts, questions? Sorry, we'll do a new questioner, and then we'll get back to our favorite repeated yes. You want to buy James Webb? I might have removed $10 billion. So cheap. Yeah, sorry. The comment was wanting to buy a telescope. So is that a question?
I don't know what my expectation should be.
So it's actually really non-intuitive. This is a fun thing. So all right. So for things like in the solar system, okay. So there's 2 axes here. There's like bright, faint. And then there's like resolving structures, like size structures. And those are 2 totally separate things. And for things that are bright, you can actually do some really spectacular stuff from a backyard telescope. I mean, in fact, looking at Jupiter and Saturn and stuff, like a pair of binoculars is honestly pretty incredible. And that's because those things are bright. They're really close to us. Where the size of the telescope, like the primary mirror size matters, is going to fainter and fainter things. And so the biggest telescopes don't actually do any better in terms of resolving, like from the ground. They don't do any better in terms of resolving structures. They just make bright things, you just collect more light from faint things. So it's somewhat depends on what you want to look at. But I'm a big telescope user, and I spent most of my grad student and postdoc years going to some telescopes in Chile called Magellan telescopes. There's 2 6.5 meter, same size as Webb, 2 6.5 meter telescopes, but on top of a mountain. In the Chilean Andes. I've spent I don't know, my wife can tell you, months of my life, a long time. I've spent a lot of time there, integrated over my whole life. One time that I was up there, they were trying to get money out of some rich donors or something. So I was up there doing science, and then they had these bigwigs come up at the top of the mountain, and they did something we never ever do with a big telescope, which is naked eye viewing. What we do is put a really expensive camera on the back, and take an exposure. But they actually set up an eyepiece on this 6.5 meter telescope, which is ridiculous, and pointed it at things like Saturn. And I got to run over and look, and mostly it just really hurt my eye because it was too bright. It didn't look any more amazing than through binoculars. It was just super bright and hurt my eye, burned my retina. So there's, that's to say that there's 2 axes, resolving structure and there's seeing faint things. And big telescopes, particularly from the ground, because the atmosphere blurs things out, they are really good at helping you see faint things. But you really don't need a very big aperture at all to see structures. So yeah, but that's also talk to your local amateur astronomer society, because I guarantee you they know more than I do about this lane of things.
You can check telescopes out at the library too.
Oh wow, there's a comment you can check telescopes out of the library, which I did not know. So everyone should do that. Thanks. That's awesome. Yeah. Question. Other question.
Lovely talk, by the way. But,
Oh.
just in something like lay language, there's project give an image of experience on the way to us?
Yeah. I did include extra slides. I don't think. So the question was, when you understand lensing, do you apply various models to understand how much mass is there? Okay, this actually might be a relevant slide. So, yes. So this might seem like an odd answer to your question. This is to show what gravitational lensing does in terms of distortions. So this is like graph paper or grid in the distant universe. If you put a typical gravitational lens in front of it, this is how it would appear. And what you're basically seeing here is anywhere that the separation, basically, so the squares in this graph all have the same size, the same area, right? If you measure the area within the distorted squares, the magnification is literally the area getting bigger. And so what we do is we try to recover what's happening. Like, we try to basically build this, a model like this, that describes how things are being magnified and distorted. And it's, yeah, as I said, that's what I said, it's a lot of work. But it's basically, and it is model-based. We know that mass deflects light, and so you basically, it's what's called a forward modeling process, which just means that it takes a lot of like computing time. You basically build a huge array of potential models, throw them into a computer, and say, build the models for all those different possibilities, and spit out the results, and then I'll see which ones agree with the actual data best. If that answers your question. The answer is basically yes. It's very model-based, it's very nasty. And the reality is there are kind of a dozen-ish people in the world who are really, really good at this. And we don't actually need more because like it's one piece of the analysis, but it's just one piece. But we need the people that do it to be really good. So I have a collaborator, Karen Sharon. She's faculty at University of Michigan up in Ann Arbor. She's the member of our team who, this is what she does for us. She does lens models and really not much else. But she's one of the best in the world. And the way that we know that she's the best in the world is she has a piece of wood. What's it called when you have like fire and you burn words into the wood? I couldn't hear anything. Charring, sure, why not? Yeah, charring, yeah. And it just says, I don't trust this model. Because that's what most of Karen says to us. Is she builds a lens model to describe the lensing for a system, then she's like, yeah, I don't trust this one. And so it took us years to kind of build up robust lens models for lots of these systems, where we really think we have a good description of what's happening.
Can you tell me about the North Star?
That it's doesn't move much in the sky.
Does it really exist?
Yeah,
Okay.
yeah, it's a star. Yeah. I mean, it's only the North Star. Its status as the North Star is temporary. It's a coincidence. It's more just that the way we do locations in space is really like longitude and latitude, right? Like longitude and latitude is a coordinate system for describing where you are on the surface of the Earth. It is an angular coordinate system because it's angular. It's basically how rotated are you around Earth, right? Like units of longitude and latitude are angles. They're not physical distance measurements. The way we measure positions in space is basically projecting longitude and latitude out onto projecting longitude and latitude out onto the sky. So you measure, and like if you're saying, all right, if I stand here and I look up, I see a star. If I tilt my head some angle, I see some other star. So there's some angular separation between them. That's how the coordinate system works. Polaris just happens to be angularly. It's located if you stood exactly on the north north rotational pole of the Earth and looked straight up, Polaris would be pretty close to straight up. That's only true for now. Like Polaris and the sun, our solar system, are both kind of moving within the galaxy. So Polaris has, fast forward.
Stars in our galaxy?
Oh yeah. Any star you can see with your eyes in our galaxy. We can only see a pretty small region around ourselves in terms of stars you can actually see. But yeah, it's just a star in our galaxy. Fast forward, I honestly don't know. 10,000 years, probably at least. Maybe not even that much. And Polaris will no longer be in that same spot on the sky. But, good luck living 10,000 years. That won't be your problem. All right, thoughts? Sure, yeah. Question was about Polaris. I guess I forgot to summarize the question first. Any other questions, thoughts, or can we? Yes.
With Webb, how many new galaxies have they found?
How many galaxies have they found? Ooh. So the question is, how many galaxies have we found? I should have looked that up. It's a big number. It's probably of order a billion, if I had to guess. I mean, that's a different statement from how many are there. And it's just that, if you look, I would guess of order a billion, but that's just off the top of my head.
So is that how much larger is that than Hubble?
Oh, well, Hubble has found a lot of those. So if you actually just wanted like a list of all the galaxies we found, the best list would actually probably come from ground-based telescopes that take shallower imaging of the entire sky. Because then you basically see everything pretty close to us. And so there are astronomical surveys that have done that. So there's the Sloan Digital Sky Survey is a famous one. There's the Rubin Observatory is going to come online. It's a big survey telescope in the south. These are telescopes that basically take uniform imaging of the entire sky. Now, Hubble can only see a tiny piece of the sky at once. So you could never do this with Hubble. It would take hundreds of years to make a Hubble image of the entire sky because it zooms in on a tiny piece of the sky. So we build other telescopes that basically capture large swaths of the sky, but much less deep. So we don't see this faint of stuff, but we see everything nearby. And so the Sloan Digital Sky Survey, this is where I'm coming. This is mostly what I'm leaning on here. I think it has on the order of like 500 million to a billion galaxies in it that it found imaging-wise. And then in Hubble deep fields, you see, we call these like pencil beams. So like the Hubble deep field, you see everything along a pencil beam super far away. Shallow survey, you see only things that are pretty close to you, but you see like everywhere. So if you want to find more galaxies, I think the more important thing is like a large volume. You want to cover a large volume, and a pencil beam has a really small volume. So Hubble's definitely found like large numbers of galaxies, but I would think that the majority of the galaxies, and these lists do exist, if you had a database of all the galaxies that we've taken an image of and given a name, where its name is basically its coordinates on the sky, that would probably be, and again, I'm fully just guessing here, on the order of hundreds of millions to a billion. That's my moderately educated guess. And Hubble's, that actually turns out mostly to be a ground-based telescope thing. Hubble's very good at doing detailed studies of like individual sets of galaxies, but not at finding like huge numbers. All right. Are all the questions? Oh, go. Yeah, go for it.
Two-parter 2.
Okay, great.
When will you have the analysis done of your data, and will you come back and report it to us?
When will I have the analysis of my data done? What are you, a grant agency? Goodness. I don't know. Oh man, how much of like the sausage do you want to know? So the way this works is when you get space telescope time, you're allowed to ask for grant funding because James Webb costs $10 billion. And so once you spend $10 billion on a telescope, it makes sense to like pay a grad student $30,000 to analyze the data. So you go to them and say, hey, give us like a few pennies. So we're in the process now of submitting budgets, which the budget that we'll get back will determine the people I can hire to work on the team. My time nowadays is all spent writing proposals, writing budgets, and then writing grant reports explaining what my team did. So it will depend a little bit on how quickly that budget process gets wrapped up. But the budget period is kind of 3 years, so we'll see. 3 years, and I'd be happy to come back sometime. I'm not going to guarantee that I'll talk specifically about that galaxy because, there could be more exciting things to say, but sure. Sure. Oh, thank you. Yeah, cheers.
Thank you. That was fascinating. I had flashbacks to astrophysics class, and I did not get triggered. I loved that class.
Everybody there's like a Stockholm syndrome because everyone loves the pictures and it's so interesting, but like astrophysics, what at least my students are, I think, beginning to appreciate is that it really does combine all of physics, and so it's one of the rare topics where you need to know like classical mechanics, quantum mechanics, nuclear physics, like thermodynamics, and it's
Yeah.
it can be a challenge.
Yeah.
But it's fun.
It's exciting. Speaking of exciting, we have an exciting program planned for you for next month on Wednesday, December 6th. So we're going to do an interactive. It's going to be a combination of educational as well as interactive, allowing you to experiment. We're going to have an artist come in and talk about color theory. We're going to have Brewmaster Brett from Urban Artifact talk about beer and coloring beer and the difference between the two, and we're going to provide flights of alcoholic or non-alcoholic, your choice, to experiment with and see if you can reproduce the colors that the experts do. So I hope you can join us for that on Wednesday, December 6th. Thank you all for coming tonight. You can follow Science on Tap on Facebook or on Meetup, and you can follow Radio Artifact on YouTube and Twitch. Thank you all for coming. Have a safe journey home.
I've always been a safe bet to grab.